Okay, good afternoon, everyone, and welcome to the plenary speech this afternoon, Energy Consumption Modelling and Forecasting for Commercial Industrial Manufacturing Operations. Great pleasure to be here, and many thanks to the conference organisers for rearranging the schedule. Originally, we were down for Wednesday, but unavoidable engagement yesterday at the UK Research Council. So pleased to be here, and thank you for attending. Okay, my name is Michael Short, Professor of Control Engineering and Systems Informatics at Teesside University in the UK. We are a modern university, post-92, very much on the applied research agenda and increasing our position in terms of research rankings. My role is Director of the Centre for Sustainable Engineering. And Tees Valley, where we are located, happens to be one of the current go-to areas related to net zero in the UK. We have a rich heritage, industrial heritage, links to the petrochemical industry, manufacturing industry, the oil and gas industry. And as part of the efforts to reindustrialize parts of the UK and rejuvenate our industrial strategy, net zero has become a significant focus within the Tees Valley region. Okay, so the outline for today, overview, some background, motivation, definitions. Then I'll try and shift the focus onto generalized modeling frameworks and abstractions related to industrial energy use. So these have kind of arose from experience of previous funded projects, where we realized that when we're trying to model and forecast different aspects of energy use, energy consumption, be it the load on a CHP plant, the load on HVAC and air conditioning systems, or most recently, the load generated by the movement of cargo in a seaport, then the models look quite differently at first glance, but we can abstract, generalize, and try and come up with a generic framework. And a local company were interested in exploiting some of these more generic abstract concepts, and we're involved in a technology transfer project with them at the current time to commercialize a prototype version of an analytics toolbox. So that's the overall thread. So our university, 3 research pillars. We are, I myself, located under the net zero pillar, principally aligned with engineering and computer science, although it's highly multidisciplinary and we engage with colleagues across the university. For example, the business school around business models, community engagement in transformative energy systems, and in the social sciences, looking at, for example, how to onboard different demographics into digital systems. So our modus operandi is engineering, research and innovation for the green digital economy. And to assist our academic research activities, we also have 3 innovation centres. One is involved with industrial digitalisation. That was part funded by eRTG. It's now fully funded by Made Smarter effort in the UK. We have the Net Zero Industrial Innovation Centre. Again, that was part funded by eRTG. The funding for that has now moved over to direct funds allocated from Research England. And we also most recently have the Centre for Digital Trade and Innovation, which is starting to look at the use of digital technologies to facilitate cross-border trade. And in the post-Brexit framework of the UK, post-pandemic, we started to see what effects disruptions to supply chains can have on lots of different aspects of our lives. And this includes aspects related to manufacturing. So as it happens yesterday, a bill got royal assent in the UK, the Electronic Trade Documents Bill. It's something we've been campaigning for quite some time. And we are the first G7, first nation within the G7 to adopt what's known as the model laws on electronic transferable records as specified by the UN. What this does, it throws out laws from well over 200 years ago, which require that the transfer of goods across a border requires a physical copy of a piece of paper, no longer. This law allows us to do that on blockchain over a distributed ledger. So the implications for supply chain engineering and net zero are significant. And again, analytics can be used and forecasting to now forecast based on knowledge of supply chains, distributed ledgers, IoT. We can do things like forecast the expected carbon footprint of the movement of goods before they even leave the host nation, the seller. So a little bit of an aside, those are the 3 innovation centers that we work with. They provide the conduit to help translate our research from labs through to prototype scale, through to commercial development. Okay, within the Center for Sustainable Engineering, 4 research themes: smart energy, smart construction, hydrogen and decarbonisation, and circular economy. My own research area, smart energy management, conversion and control. So what this is about is to take fundamentals of electrical and electronic engineering and instrumentation and control engineering, and then turbocharge them with a big dose of digitalization, IoT and Web 3.0. So within Web 3.0, new disruptive ways to operate distributed systems which are fully decentralized in nature. Cryptocurrency is a good example of a Web 3.0 technology. Traditionally, the banks hate crypto because nobody owns the currency itself. It's distributed. And the same kind of techniques and operations are starting to emerge within other domains. This is beneficial in some aspects, but it has to be controlled and implemented with care. But where this can have an impact and an influence on, for example, an energy system, a power system, is in aspects related to energy trading. And now that we don't need paper-based documents to handle bulk transfer of things like power and energy between 2 partners who both share the UN's recommended laws, then this opens up massive avenues for real-time, instantaneous energy trading between very small players. We will disrupt the big players, the energy suppliers, and push them out of the market. Disruptive technologies. IoT, Internet of Things. Well, all of us here will know Internet Protocol revolutionized computing. It enables 2 PCs or computing bits of computing equipment on either side of the world to communicate in a language that they know. If we extend that from email, web services, documentations, and so on to sensor data, control data, operational data, then we have the Internet of Things. Pretty powerful concept. So we're interested in applying these techniques to energy systems. Classical example is the use of IoT to gather data from a distributed or decentralized energy system, a microgrid, for example, process that data, curate it, warehouse it, use analytics and modeling techniques to obtain asset models of the individual items, and then use this information, these models, within a virtual environment, a digital twin, optimize them, plan, schedule the dispatch of resources, and send this information back via IoT to the physical devices themselves. So what I want to focus on today are some aspects related to modeling of these assets. And specifically, I want to try and move the focus on to manufacturing operations. So, powering future industries. When we take modern digitalization services and AI and pair them with various services which are traditionally offered within the energy sector, then we get some pretty smart outcomes which can potentially result. So smart energy contracts, smarter ways to balance a network, instantaneous energy trading, data visibility and control, supply chain management using distributed ledgers, all kinds of different aspects. Focus today is on energy analytics and forecasting. And it also builds in a certain sense, to quantifying and trading emissions and economic dispatch. Okay, a little more focus on the Net Zero Industrial Innovation Centre. Some of the work I'll be describing has been carried out within the context of this centre. A partnership principally between the university, our local authority, some aspects of central government, and TWI, the global industrial. The remit for the centre: turbocharge industrial engagement for innovation activities, principally in Tees Valley and County Durham, but with a wider outlook than that, national significance and trying to achieve international reach. The building actually opened a couple of weeks ago. If you're ever within the Northeast UK and would like to visit this facility, then please do. Innovative labs, innovative workspaces, and also a huge engineering hall with which we're prototyping several innovative projects related to hydrogen and battery technology. Okay, so some of the background, previous projects that we've worked on, which have required us to focus on energy modelling. So within the context of European Research Councils, Framework 6, Framework 7, Horizon 2020, most recently some engagement with Horizon Europe, although there are some issues with respect to UK participation, we can still actually participate at present, just not lead projects. So the integrated project, this was involved with large-scale smart grid demonstrations and had 9 demonstration sites. I was particularly involved with a demonstration site in Barcelona. A little bit more about this in due course. Dr. Bob project, demand response in blocks of buildings. Interested in modelling and control of assets, and indirectly involving humans in the loop in some cases, to achieve demand response services within blocks of buildings. So the kind of buildings that we're interested in: hospital complex in Italy, university campuses in Teesside and Romania, office blocks in France, and other office facilities in Romania. So again, this required modelling of chillers, heating, ventilation, air conditioning systems. The REACT project, decarbonisation of islands, modelling of batteries, modelling of thermal systems, modelling of power transfer and power coupling systems, and also modelling of CHP plant. Again, this cropped up in the context of the previous project, ideas from 2012. So we're starting to build up a picture around modelling. So for demand response in the case of HVAC systems, we trialled this on our own university campus. What we did was gather quite a lot of empirical data and fit that to transfer function models in order to try and capture some of the effects between the control signal and the resultant energy consumption. And of course, what's kind of the obvious thing here for any control engineer is we should be looking at the influence between the control signal and the control variable. So yes, we are, but we're also interested here in a second set of relationships: the applied controls and the resultant energy consumption. So we managed to fit several models, reasonably accurate models, linearizing around operating points, second order system with a 0, with a first order system having a 0 to describe the relationship between control signal and energy consumption. When we start to look at things within closed loop, it gets a little bit more complicated: supervisory control, set point control. But in actual reality, when we come to implement demand response in practical situations, it's the closed loop behavior that we have to model. Within the Integrity project, looked at a sports center in Barcelona, including solar panels on the roof, small microgrids, and battery storage components. And when we started to look at things like the relationship between the environmental control systems, the power that was drawn, again, start to come up with discrete time models, which could be linearized around specific operating points of interest. So various sophisticated, or we could say sophisticated advanced controls have been developed. And looking a little bit closer to home, funded project within the context of the Clean Maritime Demonstration Competition in the UK, which looks to stimulate research around decarbonisation of ports and supporting infrastructure. So working with General Electric, we published 2 papers in this conference last year on this specific project, looking at the use of digital twins integrated to microgrids technology from General Electric to explore different ways to improve energy efficiency and reduce the carbon footprint of the port's operations. And looked at lots of use cases. One of them involved identifying a model which would relate the commands applied to a joystick by the driver of a rubber-tired gantry crane, which had been electrified, to the resultant load, which was reflected back in 11 kV substation. It's huge prime movers, which lift 60-ton cargo containers around the port environment. And lo and behold, bit of investigation. I mean, these are well-known, well-studied bits of equipment. Inverters, variable speed drives to 3-phase AC motors, couplings back to the substation, the actual frame of the cargo container, a hoist with a pulley. So from first principles, you can refine things down and start to look at the dynamics and then relate the dynamics to the energy and power flows that can be observed within the substation. And we can start to come up with non-linear second-order models, which control engineers present will see classical elements, notions of nominal frequency, damping ratio, which are modulated in this case by the weight of the container that's being hoisted. And very good quality of fit in terms of the relationship between joystick commands and reflected power transients. But one thing that's all crops up in many cases as well is the use of if-then type statements. So bilinear behavior, which switches different elements, different gains into or out of the transfer function relationship, depending upon some kind of discrete state. For example, in the case of a rubber-tired gantry crane, whether we are in lifting mode of operation or whether we are dropping. So different drive motors are actuated, different gearing systems, and it changes the overall transfer function, some of the key characteristics. So observations. Emphasis on energy and power modeling of industrial assets is not quite the same as for traditional industrial control. But experience shows we can still apply modeling and estimation techniques based on variations of the structure of transfer functions. So we can look at applying regression, machine learning to a variety of different model structures, linear, non-linear, continuous, and discrete. But one thing we noticed, and this became especially apparent when looking at industrial manufacturing cells, we also need to incorporate potentially lots of discrete state information. So on-off signals, which would represent the switching behavior of various different assets. So how do we generalize some of these structures? And upon discussions, starting about 18 months ago, again with the local company Tascomp, they developed commercial grade SCADA and DCS software. They were very interested in exploring some of these aspects with us. So we applied for a Fast Start Innovation Grant. We were successful. It's a highly competitive process. Grant funding rate within the UK about 1 in 5. So for every 5 bids we put in, 1 is funded. And this one was funded. We also followed this up with some funding through the Digitalization Technology Centre that was issued. That was around looking at IoT-based edge devices to integrate in their commercial platform. So the overall idea was create devices which would allow us to non-invasively monitor power and energy of various different assets within a manufacturing site, digitalize that information, bring it into their existing system via IoT, and start to look at the development of commercial grade analytics to forecast asset and manufacturing cell consumption. So their SCADA framework, Prodigy SCADA platform, proven in a diverse range of applications throughout the UK and overseas. So a classical kind of SCADA framework for factory automation and process control. The version that they operate with now is built upon a real-time extension to Windows housed on an industrial computing platform. Extensive facilities, drivers, libraries for IoT access. Via internet protocol, that's a principal means of communication. We can bridge over and connect to Modbus, Profibus, whatever protocol we need. So what we proposed to do was to extend within this framework, not only SCADA data, but energy metering within their base platform, and separate out the historian, the operational database, SCADA information, and energy time series information. So this gives us ways to filter, pre-process, and produce clean data to a mathematical modeling procedure. So the generalization that we decided to look at was a discrete time, a fine switched linear model. So the moving average polynomials driven by these switching systems. Because we chose a linear model structure, we can then look at either batch least squares or recursive least squares to learn the correlations within some of the process signals. Okay, so yeah, classical recursive least squares, implement that in software, run it in real time. But what it doesn't really help us with is trying to understand how the discrete states influence or need to switch aspects of the linear models. So we're not quite fully where we need to be with this. Intuition plays a large part into processing the data, but we're trying to look at ways to formalize this and automate it further, looking at different ways to classify the data, group similar products, assets, services, material types into similar transfer functions, which will retain the calibration without any switching elements. So further work, very positive, lots of work still to do in this area. So where are we now? So we're at the point now where, with a little bit of help and intuition around how this cell operation classifier works, then we can produce a self-calibrating switch-defined energy use model for a manufacturing cell. So this predictive model will calibrate itself against the available data, switch based on a little bit of intuition about how we group the switches and which transfer functions are switched in and out dynamically. And it will produce forecasts which we would hope are reasonably accurate or accurate enough for the purpose that they are designed for. And as we know from a forecast and knowledge of a wider context, we can, within the framework of the SCADA system, start to optimize manufacturing operations, not just on classical basis, such as minimizing machine downtime or machine idle time, optimizing for economic costs, optimizing against a delivery schedule. We can start to optimize based on energy consumption or equivalently CO2 emissions. So for certain periods of the day, the factory will be charged more than other periods for energy consumption. For example, triads in the UK, or periods where demand response is being requested. Then we can start to optimize the schedule to reduce energy consumption at these specific times. We can get other insights from the data as well. Look at trends, forecasted trends, and decide when to carry out predictive maintenance and so on. So far we've looked at two demo sites. One is the BSW Sawmill in northwest UK, based in Cumbria. Large operational sawmill, takes raw timber in at one end, and what comes out the other end is finished products, sections of timber, which go to principally the construction industry. So annual input, over 300,000 cubic meters of roundwood. All of this is sawn to length, ground, polished, heat treated, measured, quality assured, put in batches and heads out the other end based on the orders that have been received. So company, no idea really about insights into their energy use, their energy consumption, apart from the summaries which were available from the energy supplier. So the company that we're working with, Consump, went in, installed a load of IoT meters. It was actually happened before the innovation grant was awarded. We did some preparatory work, and we managed to get fine-grained resolution of some of the individual cells or operations within the site, as well as the main incomer to the site itself. So if we take the office-based activities out of the equation and look only at the aggregated energy demands from manufacturing, then depending on the resolution, the scale with which we analyze the data, we can get pretty accurate results based on the models that we've developed. If we look at minute-by-minute readings of energy consumption, over 90% for the days that we selected for validation. But in discussion with various different manufacturers, potential end users, they specified that they would like to look at forecasts and visualizations over various different timescales. Sometimes to someone sitting in a production office, looking at minute by minute, second by second forecasts makes no sense. Makes more sense to look at quarter hour, or even 2 hour time intervals. So resampling the data and looking to reapply the techniques at different time scales produces more accurate results, because some of the natural fluctuations, some of the variance is lost as we aggregate the data and resample to longer time scales. Another case study, bench annealing of a small oven, which is in use by Tees Components. So they manufacture small steel components for various industries, including the automotive industry. They do a lot of annealing, batch annealing, the kind of situation where they would leave components overnight to a pre-programmed temperature profile. So what they're interested in is how the configuration, the choice of temperature profile would affect the energy consumption, and what the energy profile, consumption profile would look like for a typical autoclave annealing type operation. So some tests carried out on the oven, apply the analytics, again able to forecast energy consumption to around 95% accuracy based on the overall dynamics. A few switching signals need to be included, status of the door, categorization of the load inside the oven and the material type, and also the set point profile as well. But we can get good, accurate estimates of the energy consumption. So good indicators so far. So where are we taking this work? We have the paper in an associated paper, not just mine, several co-authors from the university, from our industrial partner Tascomp, and also from a colleague in India who was visiting Prof when we carried out some of the experiments. So one paper in the proceedings, another paper will present at IEEE Smart World Congress at the end of August. And this is starting to look at how we would integrate process and energy signals for energy-aware process control. So next steps, funding is critical to almost any kind of research project, especially with industrial partners. So a bit of a pipeline, got a couple of hits within the UK Net Zero Launchpad. Various aspects to this project, but a critical component is modeling assets related to battery end-of-life recycling, what the energy consumption of these end-of-life processes is, so that we can optimize and streamline the battery recycling process. That's due to start this project in September this year. And just within the last couple of days, got a hit with the Industrial Energy Transformation Fund. This is, again, applying similar techniques, looking at asset modeling for the purposes of transition to hydrogen within the food industry. A couple of large players in food manufacturing in the Northeast, links to Europe, interested in decarbonisation through adoption of hydrogen. But we need to understand what the impact is of that transition in terms of process, quality of finished product, and carbon consumption and energy efficiency. How do we redesign those assets? So some of the modeling and simulation techniques that we developed so far will be integrated within those projects. Other funded work we have ongoing at the minute related to smart cities and hydrogen on a larger scope. We're currently desperately recruiting postdoctoral research associates. There are 9 open positions, anything up to 4-year contracts on offer. Several more will be advertised over the next few weeks, and we're also after postgraduate research students as well. Be advertising some more positions later this year. So please propagate that information if you've got anyone just fresh out of a doctorate or fresh out of a master's who's looking to progress. Would be very interested in talking to them. People with backgrounds, embedded systems, IoT, machine learning, energy systems, analytics, perfect profile for the kind of people we're looking for. Okay, so that brings it to an end. Thank you for the invitation to speak and to publish the paper. And any questions?